Kari.
Good day, everyone. My name is Charles Teo and I'm from Louisiana State University. First of all, I'd like to take this opportunity to thank the committee for accepting my abstract for the AGU Conference 2013. Unfortunately, I can't be physically attending the conference, and that's why I'm doing a video right now to do a presentation about my poster for the upload to online. Thank you. The topic for our presentation is called the removal of zinc from the Wellbore return fluids. It's a project where me and my course mates did it together. Tal Lin, Siva Shankar Shamagam, Gilam Laaka, and our advisor Dr. Maleva Rajanjic. First of all, a little bit introduction regarding this project. At the early days of productions, the platforms in the Gulf of Mexico often encounter a very high zinc concentration in the wellbore return fluids, and from a few different sources, such as zinc bromide from completion fluids, zinc present in various minerals and formations, compositional zinc in casing metal alloys, as well as zinc found in perforation charges. So due to the high toxicity of zinc concentrations, the U.S. Environment Protection Agency, or we call it EPA, has a very strict regulations which only requires 5 ppm of zinc concentration to exist in the produced water before disposing it to the oceans or natural water system. So due to that, it has caused a very big burden in the platform currently. And since the reasons because that since the oil and gas company can't dispose the produced water fluids into the oceans, what they do now is they need to ship tons and gallons of these produced fluids onshore, purify them, and only dispose them into the oceans. So the downside of this process, actually, first thing is very expensive, and second is very time consuming, and it has a pretty high risk too, because it might cause a leak during the shipping process and no one will ever know. So the goal for our project is to build and design a purification system which is capable of remove the zinc ions from the produced fluids on the platform itself in the limited space. So this system is going to reduce the cost and eliminate the risk and time-consuming shipping fees of large volumes of brines. And in order to do that, we actually run a series of experiments in the lab. And this itself is the schematic of our lab setup right here. It consists of a column with about 300 millimeters in height and 25 millimeters in diameter. And in the column is packed with a certain number of resins and pass-through brine solutions. The resins that we are using is actually called the DOX 21LK XLT. This project is divided into the single column study and the multi-column study, which will go further in details later. So what happened is when the brine solution passed through the resins particles, the zinc ions actually been absorbed by the resins particles. The reason is because that the resins particles actually have a function group called the quaternary amine, which able to absorb the zinc ions and replace them with original ions. So high charges of molecules is going to get absorbed first at the beginning of the column, which is the zinc, and to the middle, the moderate charged molecules is going to get absorbed next, such as calcium and magnesium ions. And then lastly, the last charged molecules is going to get absorbed, such as sulfates. So from this series of experiments, we actually came out with the results over here. So first of all, for the single column study, we actually tested the volume of brine to the resin ratios of 2:1, 4:1, and 10:1. So first thing first, we are testing for the effects of residence time. The reason we want to do that is because we want to see how effective is the resins react towards the absorption of zinc ions. So as you can see, what we do is we made our own synthetic brine in the lab, and we run it through the column, through the resonance particles. And as you can see, the results shows a pretty positive feedback, as initially it starts from 300 ppm and drop to about 80 ppm in the first 24 hours, and then drop from 80 ppm to 30 ppm in the next 24 hours. So to further confirm our results to get a more optimum results, we actually get some sample field brine from the field, and we run it through the columns through the resonance. And this is the results that we got. As you can see, the results actually shows a pretty good declinations of the zinc concentration. At the first 24 hours, field brine number 1 actually reduced from around 8 ppm to around 5 ppm. And the second field brine reduced from 10 ppm to less than 1 ppm. And for the next 24 hours, it actually reduced even further. So this experiment shows that the resonance that we chose actually works. And for the second experiment right here, we want to test for the effects of cycles of purification. We want to see that how many cycles it actually takes for the resins to remove the zinc concentration from initial zinc concentration to less than 5 ppm in order to reach the requirements of EPA. So what we did is we take our synthetic brine and we run it through the resins for the first time, and we collected the effluents at the bottom. And then we take the effluents again and run it through a new sets of resins. And the result shows that after 2 cycles of purification, the zinc concentration actually dropped from 300 ppm to about 3 ppm, which shows an excellent results and exceeds what we expected. After that, we run a capacity test of the resins. The reason we do that is because we want to see what is the maximum capacity that the resins particles can hold the zinc ions. So what we did is we incubate the brine solutions in the resins at different point of time. We have it at 0-hour incubations, 10 minutes incubations, up to 24 hours, 48 hours, all the way up to 7 days of experiment. And as you can see the graph, every time you run the brine solution through the resins, the zinc concentration actually increases in the resins particles. And to further confirm our results, we actually take the resins particles and put it under optical microscope and we blow it out. So as you can see over here, at 0-hour incubation, this is the original size of the resin particles. And after 24 hours, the resins particles actually start to expand about 13% compared to the previous one. And after another 24 hours, the resin particles actually expand even bigger, about 21% more than the original one. As you can see over here, some resin actually show some cracks at the surface. This actually shows that the resin particles actually take off so many zinc and it actually reaches maximum capacity. So all 3 tests is considered a success. Since 3 of this single column study is a success, me and my teammates try to extend our procedures into multi-column purification systems. The reason we do that is because we want to see that if we extend from single column to multi-column, will this going to improve the absorption efficiency of zinc concentration? So for the multi-column study, the concept is very simple as the single column. We take single column and we have four of the columns and we put 4 columns at different heights, and each column is packed with a certain amounts of resin particles, and each column is connected with a flow line from the first columns to the last columns. So we run a certain number of volumes of brine solution through the first columns, and then it will go through the resins, through the fluorines, to the second column, and to the third column, and finally to the fourth columns. And the effluent is collected at the bottom of the columns. And then this is the result that we get. We send the resins particles again to be analyzed. And as you can see right here, from 0 times up to the number 6 times, it actually shows on the x-axis. And then at the 7 times, the zinc concentration start to increase, and further up to the 10 times. So this actually proved that this purification system can completely remove the zinc within 7 equivalent volumes of brine solutions, which is a very good results that we get. So, since all this test is a success, we try to extend our experimental results to the platform. And this is actually an engineering scale that we came up with. The proposed purification that we have here is very similar to the column study. This chamber is made out of 2 meters in height and 0.4 meters in diameter. It's very similar to the column that we have in our lab. And then what happened is the wellbore fluid is going to come in from a well through this channel, and then it's going to pass through the flow lines to the titanium electrode chamber, which acts as a control panel to control properties like temperature, pressure, pH, and flow rates, and etc. And then it's going to go through the flow lines to the dynamixer, and the purpose of the dynamixer is basically to prevent anything from settling down at the bottom of the chamber, and it tries to mix everything up evenly. And then from here it's passed through the first chamber into the first chamber, and we pack with resins, and the purification process is going to take place over here. And then from here it's going to go to the second chamber, third chamber, onto a series of chambers depending on the how much volumes of the proposed fluid, of the produced fluids there are. And after that, it's going to go through the bronze electrode chamber, which acts very similar as the titanium electrode chamber as a control panel. And then it's going to get discharged into the oceans. And we also have a bypass valve over here. The reason we have a bypass valve over here is because it's simply because to act as a valve to prevent the flows from falling back into the chamber. And also, is in case of any emergency, we can actually break the valve and let the liquid come out. So after that, we actually did an economic analysis comparing between the conventional methods and the zinc removal method that we propose over here. So as for the conventional method, the shipping cost is estimated to be about $50,000 per platform per month. The labor work is about $30,000 per month, and the purification method onshore is about $75,000 per month. As for all this total up add up to $155,000 per month. Whereas for the zinc removal method, the resins actually cost about $84,000 per year. Equipment to build this device, this system, is actually cost about $50,000 of a one-time fee, and others is about $30,000 for maintenance fees. And this add up to about $164,000 per year versus $155,000 per month, which actually obviously shows that this application is going to save a lot of money for the company. Please bear in mind that all these costs are estimated, as we do not have the accurate data from any companies who can provide us. So in conclusion, we know that the WX21AK XLT resins were very effective to reduce the zinc concentration to below 5 ppm, excelling the EPA requirements. And we also, from the experiments, we know that the longer incubation time and more cycles of purification is going to improve the removal efficiency of zinc in the brine. Accordingly, we also propose that the multi-phase purification system, which will provide longer residence time and larger contact areas, as shown in Figure 9. And finally, and before I forgot, please bear in mind that all these experiments are done in surface temperature and surface pressure, simply because we do not have the proper equipment and the correct environment to perform experiments for high temperature and high pressure. However, high temperature, high pH, and high pressure is a very important factors, as because that normally in the fields most produced fluids is going to be under environment of high pressure, high temperature, and high pH. So we do propose that to take temperature, pH, and pressure effects into consideration. And also, more field experiments need to be performed to verify our lab results. And these are the references that we get our research from. And we'd like to acknowledge this following people and the company that actually helped us in our project. Thank you very much. That's all of our presentation. And again, my name is Charles Teo. If you have any questions, there'll be an email address provided below. Please check it out and feel free to email me if you have any questions. I'll be more than happy to take them. Thank you very much.